Hi, I'm Woody with Line to Line Coatings.
Hi, I'm Andy Suman. Piston skirts are a great application for abradable powder coatings, one of the most important components in an engine.
Engine builders have methods to measure and fit precisely bearing clearances, ring end gaps, things of that nature, but it's very difficult to control what your final piston skirt to piston bore relationship is going to be. You now have that ability with this abradable powder coating.
Yeah, normally they measure one or two spots on the skirt and then make an assumption how the rest fits to the bore.
Right.
Now we can make the whole thing fit properly to the bore.
We'll talk about that integrated skirt clearance a little later.
The piston has a really important job in the engine. It has to harness all the power from combustion. It has to carry the rings and make a seal. And it's got to survive thermal extremes. And it's got to last a 500 million cycles in a passenger car.
The piston also has to have a low mass and they have to have a low cost.
Yes, so the self-fitting characteristics of the abradable powder coatings allow a lot of these trade-offs to be met, and you get a bigger balance window where everything works just the way you want it.
In this video, we're going to explain how self-fitting characteristics of abradable powder coating help engine performance, including life, efficiency, and the cleanliness. The pistons will fit better. They're custom fit to each individual bore. We'll reduce piston to wall clearance through our integrated skirt clearance profile. Stabilized pistons, rings are more stable, and they're going to live a lot longer. There's less wear in those characteristics for the rings. The piston's durability increases, and there's a performance benefit as well.
With stable rings, you get better oil control, keep the oil out of the fire, you get better compression sealing, so you get more power, less blow-by. That keeps your oil cleaner. So there's many feedback loops. As things get better over here, it helps over there. You also get better heat transfer. If your rings are settled down and sealed against the bore, a lot of the heat actually goes out to the bore surface through the rings. Abradable coatings on your skirt also tolerate some debris to go through without causing damage. If a piece of dirt or grit gets in here, it can either embed itself into the coating and be safely under the motion area, or it can cut a ditch through the coating and not raise those metal furrows that pierce your oil film and cause more wear.
Right, and some of that debris can be generated just at initial startup, right on a fresh bore. Some of that torn and folded material that's a result of honing your bore, we can absorb that. We're going to reduce the ability for that to become a scuffing problem.
Yeah, and scuffing in general, just due to high loading. If you have a non-metal material between your two metals, they can't weld together because there's plastic in between them.
Right.
So all this sounds a little too good to be true, but it really does allow all these trade-offs to be managed, and you get a better piston, which means you get a better engine for the life of the piece.
We have a thick coating, it wears in, it doesn't wear out.
That's right.
Let's start with telling everybody how this coating works.
So the self-fitting is what really sets our coatings apart from all the thin coatings that you're probably familiar with on piston skirts. We call it Strybeck-Hutchins fitting, and this is a little graphical depiction of what's going on. So the bottom half of this is the Strybeck curve, and this is the friction coefficient between two things that are rubbing, and it's related to the thickness of the oil film to the roughness. In other words, if you have a lot of roughness and you have a thin oil film, these asperities are going to create a lot of friction. If you have a lot of roughness and a lot of oil between them, they're not going to create much friction. So over here is where your asperities are touching. You've got a lot of friction and you can seize. That's when pistons scuff. Over here in the middle, you've got this sweet spot where you've got really low friction, and then over here, when you get really far apart, you're stirring so much oil, that adds friction too. So that's the Strybeck part of the curve. The Hutchins curve is this wear envelope. This is a high wear rate at 10 to the minus 4 and a low wear rate 10 to the minus 10. So When the asperities are touching and hitting each other, you're creating a high wear rate. If there's really not any contact, there's no wear rate. So we build the piston skirt so it's too tight. We know it's going to wear a lot in the beginning.
Right.
And as it wears, the friction drops down, and also the wear rate drops down. So as the piston keeps running, it's gonna hone itself or shape itself to the shape of the bore. Each piston in a multi-cylinder engine does this, and the wear will basically asymptotically decline. It'll never get to zero really, but it might take a million years for the next particle to come off. So when all that happens, you end up locking in the perfect geometry oil film, which is also down here where you have no wear and low friction. That's why the whole skirt can shape itself. If the coating is the right hardness and does all the right things, the piston will really form itself to the happiest spot in that bore.
When that is done, what happens to the particulate here? Is it okay in the engine?
Yeah, it goes in the oil film, in the oil.
Filter,
Anything
maybe,
big
yeah.
will get stuck in the filter.
Traps in the filter?
Anything small is just going to float
Okay.
around until your oil change.
That's good.
Doesn't hurt anything. So the Strybeck-Hutchins fitting happens at each discrete location across the skirt. Much of it starts too tight, it has to wear in, and when it stops wearing, it's got the perfect oil film thickness, and it supports the load over a bigger footprint.
Right.
So this is like a depiction of a normal piston skirt. You've got the gauge point, which is in orange. That signifies higher loading. The gauge point carries a lot of load. It's kind of the fulcrum when the piston rocks.
Right.
The yellow area would be a great oil film, and the green area is too much oil. You're just stirring extra oil that really never carries a load. So with the abradable coating, we start off, it's gonna wear quickly here, and it's gonna touch more over here. You end up with this large footprint of a perfect oil film, low friction, and now you've taken away a lot of this clearance. A lot of the green has been absorbed by the yellow, and that's what's guiding your piston to keep it stable in the bore. And it's safe. If they try to do this with the metal, it's gonna scuff.
Right. With all of that discussion, it's a wonder that we just measure on two separate points on the piston skirt when we really need to take a look at the entire surface area.
All these pistons were in the same engine at the same time. So you can see right here, the wear track is pretty thin. This other coating, it gets a little bit thicker, but with the abradable coating, look at how wide that footprint is. So that's gonna keep your piston from moving laterally, and it spreads that footprint out over a wider area. So if you take your side load and you have just one little spot carrying it on the middle of your piston, you're gonna pierce that oil film. Where if you have a large area, you got that same force, you're spreading the force out. You're not gonna get through that oil film. It's much like if you're on a lake and you're in 4 inches of water and you have a shovel, you hit the shovel and it hits the bottom in 4 inches of water. You take a snow shovel, you can swing it as hard as you want, and you're not gonna touch the bottom in 4 inches of water. That's why the big footprint is such an awesome thing for friction and wear and stability.
It's important to note that there isn't an increase in friction owing to that larger footprint with APC.
Zooming in on those same pistons we just showed you, you can see here with the thin liquid, it replicates the machine surface, and you see some scratches coming in, and this red arrow would be how far does that oil have to migrate before it gets out from between your parts and your parts can touch. So on the abradable fitted piston, you can see that instead of jumping into a machining mark and exiting, there's little pockets and they're random, so the oil has a longer path and it's not a direct path to get out from between your parts. That's a sign of a better oil film. Then you've also got all these little pores in there which are holding oil. So if you run out of your big oil wedge, you've still got oil in the coating, capacity for oil in the coating that's going to protect your parts until the oil comes back.
You know, besides the oil wedge that you're talking about, the coating has an oil holding capacity. 150x as applied, as sprayed, as we like to call it, after the surface is broken in, which we addressed earlier. Plateaus, oil pockets, perfect for a piston skirt.
Yeah, each one of these plateaus is naturally, it's machined to the mating surface that it runs against. So each plateau might be on a slightly different angle as you move around because your bore might not be perfectly round.
Exactly.
But the coating will find that fit. And then each plateau is actually highly polished. So there's no asperities to stick through the oil film, touch the mating part, and cause friction. And then each wedge or each plateau has all these nooks and crannies for oil around it. That supplies micro oil wedges to each plateau. So you've got your big oil wedge that's designed by the shape of the piston. Then you've got thousands of tiny oil wedges protecting your tribo condition.
Sure, and if the engine sees an elevated temperature cycle, for example, higher loading, then it'll wear a little bit more. We mentioned the dirt tolerance earlier.
Yeah, here's some pictures, and we've got some parts on the table too. But here's a scratch in a coated piston skirt. There's your little nice piece of sand, and you can see that it embedded. Here's another embedded one, a little lower magnification. You can get dirt, you know, sand, combustion debris, or if you have a bearing that's wearing or something, dirt comes through, it'll embed in the coating or cut through it and get safely out of there instead of rolling around, creating more third particles and more damage. This one right here, actually, you can see there's a lot of bearing material in it, all the shiny specks, but this thing ate a lot of metal, sparkly skirts. And of course, we can just blast this right off and recoat it. They can touch hone the bore, back in business instead of tearing everything up.
Extends the service life of these parts.
Yep. So to summarize what we've talked about with the Abradable on the skirt, it's self-fitting. It has mechanisms microscopically and macroscopically. The big oil wedge, it's got the little oil wedges. It finds its fit, maintains a bigger footprint. All these things help lock in the perfect shape of your skirt to each bore. And once that's done, then you've got a minimum integrated skirt clearance. Remember, that's the volume between your skirt and your bore. That's where all these extra motions can happen. If we remove that integrated skirt volume, there's nowhere for it to move, and then your rings are stable. So the next part of the video, we're going to talk about what the stable piston does for your rings, and that is really where your motor gets a lot better.
Okay, now let's consider the rings as a relationship to the bore with our reduced ISC, or integrated skirt clearance. As you can see from this graphic, which is slightly exaggerated just for the purpose of discussion, you can see that the rocking motion of the piston is going to pull your rings out of square. This is where a lot of the problems start to occur, ranging from oil control, compression pressure, and so forth. The rings are kept square to the bore. The integrated skirt clearance is filling up those gaps as best it can, and the coating is going to hold that piston more square to your bore.
Yeah, the next one zooms in a little more on the ring area, and you can see as that piston tilts, you know, the rings are trying to move into the piston. The other ones on the other side, they're moving out of the piston. Keep in mind, 3 out of 4 strokes. In a 4-stroke, those pistons have pressure pushing them against the piston. Sure. Then they got to move in that ring groove to try to maintain the seal. That's another place for wear to occur.
Right. And this relationship right here, this is the harshest contact we have. We've got a steel ring with probably a fairly hard face coating on it. It gets out of kilter. We're starting to wear on cast iron surfaces. That's where scuff starts.
Yeah, and on this side, you know, if you keep that integrated skirt clearance down, Nothing moves as much.
More stable.
These guys stay straight, they do their job better, and they last longer.
Okay, now here we have a piston top view, and of course, again, you see the relationship of the piston to the bore. We've got a gap on this side in a traditional fitted piston. You know, gap allows this motion. You're looking at it from the top, and here we are with the coated piston on the, once we have that uniform skirt coating, you know, we have less impact for the rings.
Yeah, and these arrows show, you know, you're spreading your loads out over a larger area. A little circle and a big circle touches in one place. So that's what you get, a lot of force in one area over there. So the piston shown here ran, and you can see the coating is almost worn through in this area. That area was causing scuffs for this engine builder before he started using our coating. And now you can see the coating has filled in and made a gradual transition. They never scuff again. You can see a lot of his skirt was engaged. He spread that highly loaded area across a bigger area. It works great.
This slide shows us a noise comparison in a two-stroke chainsaw. And as you can see by the graphic illustration, you have a 5 dB reduction in noise with the use of the coating.
You can really hear 5 dB difference. This graph is the same chainsaw, but it's acceleration data, and you can see the vibration that your hands are putting up with on that chainsaw is cut way down with the abradable coating. Piston's not slapping.
On this graphic, you can see the illustration. We have more torque and more power with a coated piston.
This graph is Jason Farrell's Kawasaki 600 Superbike and early data that we got from him. So you can see we're getting higher power, and we're reaching that higher power in a shorter time. On the RPM scale, you can see that through the whole RPM scale, after break-in, the coated pistons make more power, presumably because there's lower friction and better ring seal.
Yeah, speaking of Jason Farrell, there's a great shot of Jason in action. I forgot what track it is, but in summary, using line-to-line abradable powder coating on piston skirts has a lot of benefits. It's going to keep your rings square to the bore, and that's a big deal. The first indicator for a lot of engine builders are the reduced blow-by, better pan vacuum, less fuel wash, especially alcohol guys, and you know, it protects the bores and rings. Seals, better sealing for combustion.
Yeah, you burn less oil, spark plugs get cleaner.
Cleaner, sure.
You can even take tension out of your rings, your oil rings, and your spark plugs may still be cleaner than they were before.
You know, great example of running longer, and is one of my favorite product examples for line-to-line. This is a Trans Am piston. This is 4 races. 4 races in, the piston skirts look beautiful. The Total Seal guys looked at this and said, you can run the rings again. That's pretty good.
So if you read between the lines here a little bit, you're gonna save a lot of money using abradable powder coatings on pistons. You can restore the size, get your clearances better than a brand new piston. Even if your bores are overbored by a couple thou, you got a touch hone, so now you're not buying new pistons, waiting, rebalancing stuff. You just hone it out, we recoat them, you put it back together and go.
There's an economy to that. People generally in the past haven't used pistons a second time. If your ring lands are good, your pin bores are good, which they're going to be using these coatings, you can use them again. Send them to us, we'll remove that used coating if you please, and coat them again, and off we're going.
Yeah, we've had a lot of guys that had some problem happen. You know, maybe an injector goes bad. They
One cylinder.
burn a cylinder down and they'll call up and go, I can't believe it. I think that coating saved my block.
Sure.
So there's a lot of ways to, you know, spend more on tires and less on engine parts.
Best insurance you can get.
Yep. So we want this to be a new tool for your toolbox in your engine programs and pump programs for that matter. Development, you see a lot of stuff, you get witness marks, it helps you figure out what you want to do. Race, you can push things harder, be ready for the races, smooth operation, heat, RPM tolerance. It also lends itself to high volume production. This is not just a boutique process, this is scalable to millions of parts. And then restoration, that's really fun. Woody.
Restoration's a big deal. I don't build racing engines anymore. I rebuild 1910 antique farm engines, and this coating has saved the life of many of them.
So thanks a lot for watching.
Thank you.
Please go to line-to-linecoatings.com for more information, and thank you very much.